Good afternoon, students. I hope I am audible and the screens are being shared to you. Alright, so the previous session we discussed about the concept of oscillator. Okay, so we had seen that oscillators are mainly based on positive feedback. They produce periodic oscillating signals. Most oftenly they will be of sine or a square wave type. They are mainly used in clock generators, calculators and the other computer peripherals. They are often characterized by the frequency of their output signal, and we can distinguish the oscillators mainly by two types: linear oscillators and non-linear oscillators. We will be focusing on linear oscillators with respect to our syllabus. Okay, and we had also discussed about the Bar-Cousins stability criteria. So this is the main criteria on which most of the oscillators are based upon. Okay, there are two criterias. The first one says that the overall phase shift around the loop from input to the output in an oscillator circuit must be an integral multiple of 360 degrees, and further the open loop gain must be equal to 1 in order to produce sustained oscillations. Okay, so that was the block diagram of a oscillator circuit. So you have an amplifier and you have a feedback network. The feedback signal which comes out of the feedback network will be in phase with respect to the input signal. Okay, so when both of them are in phase, we can say that the feedback is positive. Else if they are out of phase, then it will be a negative feedback, right? Okay, and most importantly, this parameter beta into A is called as open loop gain. Okay, so we had seen how to initiate the oscillations in the case of an oscillator, right? Initially you will have to supply a small input signal. Most oftenly the small input signal will be a noise signal itself. Okay, so the oscillator circuit, it considers the noise signal itself as the input, and it just amplifies the signal, and then that particular signal will be taken back through the feedback, and from there onwards the feedback signal will act as the input signal. Okay, so that as and when the number of feedback stages goes on increasing, the gain also goes on increasing. Okay, so you can clearly observe that here after each and every stage you can observe that the amplitude of the oscillations being produced are slowly increasing with respect to the time. Okay, so here the condition being satisfied will be beta into A greater than 1. Okay, so this is at the initial stage, but slowly with respect to time the loop gain will settle itself such that it is equal to 1. Okay, so when this condition gets satisfied, the amplitude of the oscillations begin to saturate, in the sense they are of same amplitude. Okay, so further we will be getting such type of signals which are of constant amplitude and the same frequency. Okay, right. So that was how the oscillations initially build up and then finally attain the steady state. So depending upon the condition of the open loop, there are three conditions. So based upon those three conditions we can differentiate or distinguish the oscillations in three types. The first one being sustained oscillations, and we had seen it, beta A is equal to 1, and here the sustained oscillations will be of constant amplitude and the same frequency. If beta into A is greater than 1, then the oscillations will be increasing with respect to time. Okay, they just increase exponentially, right? In terms of stability, we do not prefer exponentially increasing oscillations, because although the gain increases here, correspondingly the stability decreases, okay, which in turn it actually deteriorates or affects the particular circuit. Okay, so such type of oscillations are strictly prohibited in the case of negative feedback amplifiers. Okay, they are only preferred in the positive feedback circuits, that too in specific and particular applications where it is necessary. Then further, when beta into A is lesser than 1, we'll be getting damped signals, so that initially the signals will be there, and then finally as time progresses the signal completely dampens out or decays. Okay, so those three are the different types of oscillations being produced by oscillatory circuits. Okay, so today we shall be discussing on some of the practical based oscillators, okay, which are also commercially very popular. The first one is called as RC phase shift oscillator. Okay, now before we proceed to practical based oscillators, in the last class I had also mentioned about the nature of the feedback circuit. Okay, so if we consider this to be an amplifier and the second block to be the feedback network. Okay, so the concept of oscillator is very simple. Without any input you will be getting an output signal, provided the Bar-Cousins criteria are getting satisfied. So at the output side you should have the output V0. Okay, now amplifier, generally it is a single stage RC coupled amplifier. Okay, so we'll be talking about it later, but a single stage RC coupled amplifier provides a phase shift of 180 degrees. Okay, the output when compared to the input has a phase shift of 180 degrees, and it also gets amplified. Now as per the concept of the oscillator and the Bar-Cousins criteria, the phase shift should be either 0 degrees or 360 degrees or an integral multiple of 360 degrees. So in order to obtain 360 degrees, what should be the condition? The amplifier provides a phase shift of 180 degrees, then the feedback network must provide a phase shift of another 180 degrees. Now what are the components present within a feedback network? Usually the components are a combination of RC or LC. Okay, so by using these two components we can get the necessary phase shift. Okay, so the necessary phase shift of 180 degrees can be obtained. Okay, so now the first type of the feedback network is RC. Okay, so if we use RC as the feedback network, then collectively we can call the particular oscillator as RC phase shift oscillator. So the slide presents the complete circuit of a RC phase shift oscillator. So let us just go through it. So this triangular one, the triangular block represents amplifier as usual. So as I had mentioned, usually this is a RC coupled amplifier. Okay, I hope students know something about RC coupled amplifier. Okay, you must have studied it in your basic electronics, a single stage RC coupled amplifier. Okay, then so this provides amplification plus a phase shift of 180 degrees. Okay, now so let us call this as intermediary output V0. Okay, so this V0 is being taken and then fed to the feedback network. So the blue color highlighted rectangular box is the feedback network. So here the feedback network consists of a combination of R and C's which are in parallel. Okay, now there are 3 RCs in parallel. Okay, so if you just apply the basic network analysis, then it will be easy for us to understand that one single RC in parallel is capable of providing a phase shift of 60 degrees ideally. Okay, this is what we are talking about. Ideally, one RC, a combination of a resistor and a capacitor, can provide a phase shift of 60 degrees. Okay, the mathematical derivation of it, students can refer any of the basic electronics textbooks, okay, wherein you will very clearly see it. Okay, by the network, by the concept of the network analysis, it will be derived. Okay, so one RC, if it provides a phase shift of 60 degrees, then the second one is also expected to provide a phase shift of 60. Similarly, the third one, okay, 60 degrees. So that altogether you will be getting a phase shift of 180 degrees, and this is what we need, right? The amplifier provides a phase shift of 180 degrees. Feedback network provides a phase shift of another 180 degrees. So that collectivity altogether it becomes 360 degrees phase shift. So that the first criteria of Barkhausen's rule gets satisfied. Okay. Now this is theoretically, but practically most oftenly due to loading effects. Whenever we say loading effects, it's like, you know, a combination of R and C. Okay, this exerts some loading effect on the second parallel combination of R and C. Similarly, the first and the second one exert further loading effect on the third RC, due to which it is very difficult for single R and C to provide exactly phase shift of 60 degrees. Theoretically it is possible, but practically it's very difficult. Okay, so what matters is altogether collectively, okay, collectively, if you know the first one provides a phase shift of 58 degrees, okay, for example, in the second one, okay, if it provides a phase shift of, you know, further 60 degrees, say for example, then the third one will be providing a phase shift of, you know, 62 degrees. See, this is practically, okay. So the point is altogether somehow we have to obtain the phase shift of 180 degrees. Okay, fine. So that was one very important point about the feedback network, which consists of 3 parallel R and C's. Then, so what do the statements say? Using network analysis, the attenuation of the network at a frequency at which phase shift is exactly 180 is given. All right. The frequency of the oscillations, you know, this is extremely important, right? Okay. The frequency of oscillations of the particular RC phase shift oscillator depends on this particular expression, 1 upon 2 pi RC square root of 6. Okay, generally it will be 1 upon 2 pi RC, but because of this particular 3 RC components, you have this additional term square root of 6. Okay, further again mathematically it can be proved that the beta factor, the feedback factor, is 1 upon 29 for this particular circuit. What does that mean? You know, 1 upon 39 is approximately 1 by 30, okay, which means it's, you know, as good as 0.03, okay, roughly. You know, that's the maximum feedback factor that you can take. Now the problem is the Barkhausen's criteria states beta into A must be equal to 1. Okay, now if beta is 1 upon 29, then what about the gain of the particular amplifier? Okay, this amplifier, this must be 29, right? And initially for the oscillations to start, just beta into A equal to 1 is not sufficient. it should be greater than 1, okay, because the oscillations have to begin, right? So to ensure this condition, again the amplifier gain must be greater than 29. What do we mean by that? This particular amplifier must be capable of amplifying the input signal by at least greater than 29 times with respect to the input signal. Okay, in turn, what does that mean? An amplifier consists of transistor, right? It could be a BJT, it could be a JFET, it could be a MOSFET, whatever, okay, but basically it's a transistor. Now that particular transistor must provide amplification which is at least greater than 29. So what all parameters must be taken care of? For such condition, the biasing should be proper. Okay, again, we'll have to go back to our DC biasing, then the AC analysis. Okay, so it's like one step backwards, okay, another step backwards. Okay, so it all starts with the device itself. The device must be properly chosen, then the DC biasing must be properly done so that the Q point is proper, it is stable. Further, the gain should also be at least greater than 29. So all these parameters do matter when it comes to the design of a particular oscillator, especially the phase shift oscillator. In this case, it should be greater than 29. So I hope the things are clear to you now. Alright, so what does the last statement say? It states the total phase shift provided by all the 3 RC sections must be equal to 180 degrees. Yes. Alright, so that's what the internal structure of this amplifier. Okay, so here it is just a triangular box. What will be present inside the triangular box? If we use a FET, then this is what the amplifier section is. Amplifier, okay, with a JFET. If we use a transistor, this is what is the amplifier section. Okay, so this is amplifier using a BJT. Okay, right? So if it is a BJT, then this combination is a RC coupled amplifier. So I'll just write it is RC coupled amplifier. Okay, and the biasing is voltage divider bias. Hope you can remember, because we have R1 and R2. So this is a voltage divider biasing circuit that is being used in this particular amplifier. What about the amplifier with the JFET? Students, can you just recognize the biasing circuit? This is a self bias circuit. Okay, so that's a self bias configuration, right? And as usual, this shaded portion is again the feedback network, 3 RC sections. Okay, so similarly here also, okay, that becomes our feedback network. Okay, so if you just go through the formulae, with JFET it is 1 upon 2 pi RC square root of 6. If it is with a BJT, then there is a small change, and that is 1 by 2 pi RC multiplied by the factor 1 upon square root of 6 plus 4 RC upon R. Okay, so since we are not studying the amplifiers with respect to BJT, at least in your theory, we'll try to ignore this using the BJT, and we'll also forget this particular formula. Okay, however, this is important when it comes to your lab. Okay, now what is important for us is with respect to BJT, so this formula is important for us, 1 upon 2 pi RC square root of 6. What about the amplifier gain? The magnitude is given by the gain factor A equal to the product of transconductance multiplied by RL. And what is RL? RL is the parallel combination of the drain resistance multiplied by the internal resistance, small rd. So it's capital RD, small rd, which are where both of them are in parallel. Okay, so that is the gain factor. Right, now you can just think a bit. The condition was that this A must be greater than 29. Right, so to ensure that, what we'll have to do, see, RL is the combination of two parallel resistors. One is an external one. Okay, see, please understand that RD is the drain resistance. Okay, and it's a passive external component. Okay, so we can select it. Okay, we can choose it. At the same time, the small RD is the internal output resistance associated with respect to JFET device. Right, and it is fixed. We cannot change it. It is being decided by the manufacturer itself. Right, so that is JFET's output resistance, and that is fixed. We cannot change it. What can be changed is only this drain resistance RD. Okay, and similarly, what about GM? GM is also fixed. Right, it is also fixed by the manufacturer. Okay, because its value is being given in a spreadsheet, so this is also fixed. Right, so now the point arrives, how can I change the gain? If I want to change the gain, the only parameter with which I will have to play is the drain resistance. Okay, so I hope this point is clear to you, students. Right, okay, so that was all about phase shift oscillator, RC phase shift oscillator, which either uses a JFET or a BJT. Okay, now one more point to add here is, what will be the output like? Okay, where is the output? The output is at this point. Okay, if it is a JFET, then it will be across the drain. Okay, either here or here, any point. So this is the output. Now how will the output appear like? The output, if the Barkhausen's criteria gets satisfied, then we'll be getting sustained oscillations. Okay, and on what parameters does the amplitude of the oscillations depend upon? Okay, or to put the question in another way, how can I increase or decrease the amplitude of these oscillations? Well, the first point is, if I vary the DC supply VDD, okay, which controls the biasing, then I can just control the amplitude of this particular thing. And the second point is, even if I vary the resistors of this particular feedback network, then I can just vary the phase shift of this. Okay, and even if I vary the drain resistance value, I can to some extent control the amplitude. Okay, vary the amplitude of this particular oscillatory circuit. Okay, so students, once you really get into the lab and you just try out these experiments on your own, then I am pretty sure that you will really appreciate the fundamentals, okay, which are behind these things. Okay, you can very clearly observe these things, the changes happening on the CRO. Okay, once you construct the circuits on your own. Fine. The next type of oscillator is called as Wein bridge oscillator. I hope you have already heard about this term, Wein bridge. Okay, how does it look like? We'll just see here in your textbook. Okay, instead of a JFET, they have used an operational amplifier. Okay, so you can either use an amplifier or an operational amplifier. An operational amplifier is just a specialized amplifier. Okay, it again consists of the same transistors, the same active and the passive components, but the only difference is that it's a specialized amplifier which can perform much more functions, much more operations than a normal amplifier can perform. Okay, fine. So what or how does a Wein bridge oscillator look like, and what all does it consists of? It consists of an operational amplifier. In short, operational amplifier is being called as op-amp. Okay, OP stands for operational amplifier. And then a RC bridge circuit. Okay, well, we are comfortable with this RC bridge circuit, right? Because I hope you must have seen this particular bridge network even in your network analysis, Wein bridge. So you have an op-amp, an RC bridge circuit with the oscillator frequency, which are mainly set by R and C components. Okay, so resistors R1 and R2. So where do we have these resistors? Let us just go to the circuit. How does it look like? Okay, so just observe here. You have a operational amplifier. Okay, it's nothing but a specialized amplifier which has more control, right? So this is an amplifier, and that's your feedback network. Okay, so in the feedback network, in the complete Wein bridge network, what is the purpose of each and every component, each and every passive resistor and capacitor? Okay, let us look. Because you have R1, you have C1, you have R2, C2, you have R3 and R4. So there are 4 resistors and 2 capacitors. Let us just look at those things, their role. Resistors R1 and R2 and capacitors C1 and C2 form the frequency adjustment elements. Okay, so the frequency adjustment is being made by the combination of R1 and C1. So here they are in series, and this combination also. So one RC is in series and another RC is in parallel. So these two sections, right? Okay, so they help in frequency adjustments of the oscillatory circuit. Frequency adjustments. Similarly, what about the resistors R3 and R4? They form part of the feedback path. So this R3 and R4, okay, both of them form path of feedback path. Okay, next, the op-amp output is connected as the bridge input at points A and C. Okay, so the op-amp output is connected as bridge input. The op-amp output is connected at the bridge input with respect to points A and C. Similarly, the bridge circuit output at points B and D is the input to the op-amp at points B and D. Okay, please understand, this entire thing is called as Wein bridge network. Okay, so let me just write it here. This is called as Wein bridge network. Okay, it resembles like a bridge network, so it is called as Wein bridge network. So the points B and D are connected as inputs to this particular op-amp. Okay, so this forms the feedback or the output path which is being given to the feedback network. Okay, so I hope the purpose of each and every component in this particular circuit is clear. R1, C1, R2, C2 form frequency adjustment elements. R3 and R4 form feedback path, and the output of the amplifier is connected to the points A and C, and the points B and D of the Wein bridge network are connected to the input of the operational amplifier. Now, neglecting the loading effects, okay, we'll have to neglect them, of the op-amp input and the output impedances. The analysis of the bridge circuit. See, loading effects always reduce the gain. Okay, if there are loading effects, why do these loading effects add up? I had just discussed that if there is a combination of R and C, and if this is followed by another combination of R and C, okay, then the effect of the first stage, okay, it also adds, or it puts some loading effect on the second stage, okay. So due to which the overall performance of the network gets reduced, but we'll have to ignore them as of now, okay. So neglecting the loading effects, how can we analyze the bridge circuit? By this particular expression, R3 upon R4 can be given as the summation of two expressions, two subterms, where the first term is R1 upon R2, the second term is C2 upon C1, okay. So it's good to remember this particular expression. Then what about the frequency of oscillation? FO stands for oscillatory frequency, is given as 1 upon 2 pi square root of R1 C1 R2 C2, right? Because R1 C1 and R2 C2, they are the resistive and the capacitive elements which are responsible for the adjustment of the frequency, right? Okay. Now how do we simplify this? We can simplify this by assuming R1 equal to R2, right? And similarly C1 equal to C2. C1 equal to C2. Then the equation gets much more simplified, and this is what the expression results. F naught equal to 1 upon 2 pi RC, right? And okay, so these are the simplifications which are being done. Then a ratio of R3 to R4 greater than 2 will provide sufficient loop gain. Yes, this is one condition which is being taken care in the case of Wein bridge, just to ensure that there is sufficient loop gain. So when R3 upon R4 equal to 2, then you will have sufficient loop gain so that the circuit will oscillate at the frequency calculated. Okay, so that is one added term here. Okay, fine. So that was all about Wein bridge oscillatory circuit. So again you will be getting sustained oscillations at the output side. Okay, so this also can be verified in your laboratory, right? So you can observe that in both RC phase shift oscillator and Wein bridge oscillator, the feedback network comprised of simple R and C components. Okay, all right. Now there is a small problem with respect to RC components, and the problem is tuning cannot be made properly. Okay, the phase shift cannot be controlled properly, and the tuning of tuning of the output at a particular frequency is not so easy in the case of RC. Okay, so this can be better controlled by replacing RC with LCs. Okay, so all that we can say is RC is simple, but it is not so efficient, with respect to tuning, with respect to frequency tuning. Okay, so if we want a better tuning circuit, then we'll have to go for a combination of L and C, where L stands for inductance and C stands for capacitance. So if we use L and C, it is called as a tank circuit. Okay, so if we use a tank circuit, then we'll be getting some more combinations of oscillators, which we will be discussing in our next class. Okay, so just for your practice, there is a problem on a Wein bridge oscillator circuit, where again certain parameters will be given and you will be asked to find out the frequency of oscillation. So it is again a simple substitution based problem. Okay, you can go through it, right? Similarly, okay, see, if you get a problem of this kind, then either R and C values will be given. Okay, if R and C values are given, then you will be asked to find out the oscillatory frequency, or sometimes we may give you the frequency of oscillation and maybe either R or C value, and then ask you to find out the other component value. Okay, so again they are simple substitution based problems. Okay, the same thing, design the values of R and C elements. You will have to you will have to assume one value and then find out the other value, as simple as that. Okay, so try to go through this problem, and in the next class we'll try to discuss about tuned oscillator circuits and also crystal oscillators. Okay, fine. So any doubts, students, you can ask me.